Recording in progress.
All right, so this is supposed to be some supplementary material just to assist you on some of these optimization problems. Maybe you just needed to see a few more examples worked beyond just what we did in class and what we have in our text. So this one, we're going to start off pretty easy. We're just going to find the dimensions of a rectangle with perimeter 100, specifically meters, but more often than not, we're worried about the number, not the unit. And what we want to do is we want to maximize area. So let's sort of figure out how this should look. Well, I got a rectangle, looks something generally like this, maybe I'm going to call this width is really long. Maybe the length is really long. But the point is that, this is its general shape. And we know that associated with it, we have a width and we have a length. We also know that we have a perimeter to this rectangle. Specifically, okay, well, I got this side length from the width up here, the width down here. Okay, well, that's 2W. And then I also have this length here, I get a 2L. And beyond that, I also know that whatever these two side lengths are, they have to equate to be 100. Okay, makes sense. And beyond that, I also have that the area of the rectangle is length times width. Now, I don't know what area is because I don't know what the side lengths are. But using this nice perimeter equation up here, what we can do is we can solve for one variable in terms of the other. And then we can get area to be something dependent upon one variable. And then we can do the fun calculus part. So first things first, knowing that area is perimeter is 100. And we have that 2W plus 2L is equal to 100. Then, well, we also know that 2W is equal to 100 minus 2L. Or, if we divide both sides by 2, then what we should get here is that W is equal to a 50 minus L. So keeping that in mind, what that means is that now we can make it so that area only depends on W, our width. And basically the way we do that is, well, we can replace, I solved for W in terms of L. So instead of making this a function dependent upon width, I'll actually be making this a function dependent upon length. My bad. But the main idea is that one of these is going to have to get replaced. Since we solved for W in terms of L, well, that's what we're replacing, right? So far, here we are. And now we'll move on to distribute it. All right, now we've done our little distribution and we found A entirely in terms of L. Now we do the optimization process. And to do that, what's the first thing we got to do? We got to find our critical numbers. Now, luckily, I don't really have to worry about this function becoming non-existent, as far as its derivative goes. Because when I derive, this first term, well, all I get back is that 50, just using our power rule. And then for our second term, all I'm doing is I'm subtracting out 2L. No real opportunities here to get a domain error or a divide by a zero error, anything like that. Oh, went a bit too far. Now, continuing on with our derivative, the only other option to get critical numbers is to set the derivative equal to 0. And the derivative is going to equal to 0 whenever 50 minus a 2L is equal to 0. Makes sense, right? Just looking back at our formula for the derivative. Well, if I wanted to, I could just bring that constant over to the right. Then I could divide by a -2 and get that, okay, well, length is 25. So whenever length is 25, we get a critical value. But likewise, if I go back up here and I start replacing all these equal signs with less than signs, what happens? Okay, well, less than still here. It's still less than here, but now because I divide by a negative, it flips back to be greater than. So this is going to be negative whenever L is greater than 25. Now, what about positive? Okay, well, I start things off. First, I'm greater than. Okay, still greater than, but then I got to flip less than. So basically, what the first derivative test is now telling us is that A has a maximum at L equals 25. In fact, it's an absolute maximum. So what we do is we just plug in 25. Wait a minute. We don't have to plug in 25 to our area, right? Because all I'm worried about is is this the maximum area? Well, yeah, it's definitely the maximum area. But I'm not asking you what the area is. I'm asking, well, what are the dimensions? So really, now that I know L, all I have to do is find W and I'm done. And so what we're going to be doing is we're going to be using this equation. This W equals 50 minus L. So, we don't have to find that. But what we do have to find is W. I know that it's 50 minus L. I mean, sorry. Yes, no, 50 minus L. And we know that A is maximized when L is equal to 25. Thus, W is equal to 25 when the area is maxed. Makes sense, right? Just subtraction. So the dimensions of this rectangle are a width of 25 and a length of 25. So it's actually a square with side length 25. And now we will go on to the next question. So believe it or not, in my opinion, I think that this next question is actually a little bit easier, personally. But I could see why it's not for some people. So basically, what I'm going to draw here, well, not draw, but what I'm going to write here are some nice cost and demand functions. If you see me draw a little tail like that, that just means it's a lowercase p, and thus it's our demand function. So let's suppose that our cost function, the cost of production per unit, is say 200x, something like that. plus maybe, a little bit of startup costs. And let's suppose that our profit, sorry, not profit, but our cost function is something like, an initial cost minus, say, just a little bit of money as we ramp up production. Now, the thing about these two functions is that they don't really tell the whole story. What we have to recall is that revenue is equal to X times that demand function. So keeping that in mind, okay, well, X stays where it is, but now I can replace this demand function into these parentheses. Okay, then I can distribute the X. And that's our revenue function. Now this capital P function is our profit function. And what we have to remember always is that by definition, profit is revenue minus cost. Keeping that in mind, we just replace these functions into this formula. So for R, I get a 400x minus a 1 over 10 x squared. Then for our costs, okay, well, remember, I'm subtracting out. So I'm going to be subtracting out this 200x, and I'm going to be subtracting out that 100. After that, well, it's just like terms, really. So I still have a positive 200x. I got that negative 1 over 10 x squared. And I got that negative 100 there. So keeping that in mind, well, this is the fully simplified version of our profit function, but that's not really answering the question, right? We don't just want the profit function. We want to figure out, okay, well, how do I maximize it? Well, to do that, you need to find your derivative and talk about extrema again. So I take my derivative. On the first term, simple power rule, we're left with a 200. For the next term, another power rule. I'll be left with a 1 over 5, reduce the power, I have an x. And then a constant always vanishes. Now, I think we can all agree that this derivative is never going to not exist, right? Basic polynomial. No divide by zero errors, no domain errors, nothing like that. So, yay! All we have to do is find out when the derivative is equal to 0. And that is going to happen whenever we have 200 minus 1/5 x equaling 0. Or, we have a 200 equaling a 1/5 x. So this time I put the x on the right. I kept the number on the left. Habit of mine, whenever I see something negative, I usually add to get rid of it rather than keep negatives on the left, but I'll try to avoid this little conundrum in future problems. Now, if I wanted to isolate x and get it on itself, what I'd have to do is I'd have to multiply both sides by 5. And if I multiply the left by 5, I'll get 1,000. Multiply the right, I'm just left with x. Right? So, that being said, if we go back up here in our work, then let's figure out when profit is negative. So, I'd be keeping a less than sign here, less than sign here, less than sign here. I never had to flip it because I never divided by a negative number. So basically, the derivative is negative when 1,000 is less than x, where x is greater than 1,000. Likewise, if we go back up in our work, this greater sign never changes position, never gets flipped. So what we have is that 1,000 is greater than x. So what we have now is that x is less than 1,000. So this is something that should have been intuitive to us because we know that it's a downwards parabola, but what's happening is that we're increasing to the left of 1,000 and we're decreasing to the right of it. So what that means is that P, our profit, has an absolute max at x equals 1,000. Now, are we done? Well, let's look back at the statement. Given the following cost and demand functions, all I had to do was find the level of production maximizing profit. Well, I found a critical number. I determined that I get a max there. I found the level of production. We get to call it a day this time. Now, last but not least, something just a bit tougher. Something that isn't, a basic area formula. Something that just takes a bit more intuition. It takes a bit more time to model it. So let's sort of just outline this question. The top and bottom margins of a poster are 3 centimeters. The side margins are 2 centimeters. Whoa, 2 centimeters. Now the area of the printed material on the poster is 96 square centimeters. We want to find the dimensions of the poster with the smallest area. So what we want to do is we want to find dimensions. And what we want to do is we want to minimize area of the poster. The stuff that's printed on the inside of the poster, well, that's a fixed area. That's 96. But the margins themselves, they're also fixed, right? Yet, what do we have to sort of like vary here? Well, let's draw our little poster. So, in the center of it, I have a little printed material here. I got a nice little rectangle, square, something with, a nice little 4 sides to it. Because I have margins on the side, each measuring 2 centimeters. And I have these margins on the top, each measuring 3 centimeters. All that's fixed. And what I also know is that the area of this inner rectangular square, whatever it is 96. What I don't know are these 2 side lengths. I know that there's definitely a side length here. I definitely know there's a side length here. I don't know what they are. It could be that I squeeze down Y and I make it a really, really short rectangle. Or I squeeze down X and I make it a really, really thin rectangle. There's a lot of options here. As long as I keep these margins the same length, well, I satisfied my duty. provided I've also, kept the area of this inside rectangle the same as well. So now that we sort of have the picture in our head, let's figure out the formulas that we have available to us. So the area of the inner rectangle, i.e., our printed area, well, that's equal to x times y, but it's also equal to 96. What we want to do is we want to optimize the area of the outer rectangle. Whoa. i.e., our printed material. Oh, wait, sorry, not our printed material, but our entire poster. So this is the poster. Now this one's a bit tougher, but I think that we can figure out what exactly this area formula is. Well, all right, well, this is one side length. This is another side length. Let's figure out what these measures are. Okay, so I know that for this horizontal line here, I have the X, right? That printed material. But then I go out, include this margin. Okay, well, I'm adding on 2 here, but I'm also adding it on over here. So the net total of this side length is X plus 4. Now, what about this side length that's going up and down? Well, I have the Y. I'm adding a 3 up here, but I'm also doing it down here. Take that together, I'm adding 6. And so the area of our outer rectangle, i.e. the entire poster, is X plus 4 times a Y plus 6. But then I could do a little algebra, right? First things first, distribute the X to the Y. We get an XY. Then distribute that X to the 6, we get a nice 6X. Here we get a 4Y. And then a 6 times 4, well, that should be a nice 24, right? Now, luckily, we don't even have to stop there, because what we have is right here. X times Y is equal to 96. So what can I do with this first term? I can just replace it with 96. Then, okay, well, add that together. And the area of the poster in terms of X and Y is the following. Now, sadly, I can't do the optimization yet, right? What we have to do is we have to use this equation up here for the area of the inner rectangle to get the following area of the outer rectangle in terms of just one of these variables. I think that most of us like X a bit more than Y. So what I'm going to do is I'm going to solve for Y in terms of X. Well, X times Y is equal to 96. So Y is equal to 96 over X. Thus, the area of our poster, if I just look back at the formula real quick, is 120 plus 6X plus a 4Y. But now, to get it all in terms of X, we just replace. And now we just do a little bit of, arithmetic. So 96 times 4 should give you a 384. And this is still over x. So now we have the area of our poster all in terms of just one variable. So keeping that in mind, now it's time for the optimization part. We take our derivative. First term vanishes. The second one, simple power rule, uses we just have 6 left. The next one, keep in mind that 384 over x can be written in the following way. So it's still a simple power rule. It's just, okay, well, now it's a negative power. But this is something that, we should be very familiar with by now if we're talking about optimization. So what we'll have now is an x squared in our denominator for the derivative. Now, if we look at this derivative here, I think it's pretty clear that right away, okay, well, a prime does not exist when x equals 0. But I mean, that's not even really in our domain, is it? It's not like I can have a poster of area 0 when I have that the printed material itself is already a positive area. So this is sort of like, a boring result. It doesn't really help us out in our, work. So the fun part here is going to be, well, setting this equal to 0. Now, what we could do is we could take both terms under a common denominator, or we could just leave it as is, set it equal to 0. In class, I did the common denominator, but this time I think I'm just going to set it equal to 0, because all I have is just 1x under there. Well, sorry, 1x squared under there. It's quite easy to solve this just using cross multiplication. So the derivative here now is equal to 0 when 6 minus 384 over x squared is equal to 0. Okay, well, this time I'll try and be nice, keep the x's on the left side. Now I got a nice -6. So I'm just rewriting what we had on that last slide. Well, I think that everybody knows from, our middle school days working with fractions that if I have the left equal to the right, okay, well, I can flip the fraction on both sides. And they're still equal to one another. And I mean, luckily for us, both sides are negative. So I don't even have to worry about that sign change there. I can just cancel it out on both sides. Now to get x squared by itself, I just multiply both sides by 384. Now, once more, simple arithmetic. 384. Is that going to be divisible by 6? Well, it's even, and yeah, it's divisible by 3, so I'll just divide it by 6. We get a nice 64. Now, finally, x itself is going to be equal to a positive 8. Just taking the square root on both sides. Now, what I want to stress here a little bit is that we're disregarding that -8 they usually get in like a standard solving the roots of an equation. Just because we're talking about x as a distance. So it wouldn't really make sense to talk about a negative distance. Ergo, we only really consider the positive root in this case. Now, we found the first dimension, right? So let's go back to our original question. We wanted to find the dimension, right? Well, I found a dimension that gives me a critical value, Let's verify real quick if it's an absolute maximum or an absolute minimum. Because if it turns out that this gives us a minimum in our area, well then, great, we're pretty much done. Just, after this, all we have to do is find y. If it's not a minimum, okay, well, sad day for us, Now, to figure out if it's a minimum, because we don't have a nice closed interval, okay, I can't use CIM. I have to use FDT. But to be honest, if we just look at our work again, okay, well, starting from here, there was no negativity that I did, right? So I still had that less than. Now what happens over here is that when you flip both sides and they're reciprocals, okay, well, then the inequality sign once more changes, But then I multiply by a negative, okay, well, it flips back. Still there, I multiply by a positive number. And so when I have that square root on both sides, okay, well, this would be a less than. So we're going to have that our derivative is negative when x is less than 8. Oh, gosh. All right. I think that's fine. And just like I did before, this time think about it in your head. If instead I put those nice blue greater than symbols, how would they change in our process here? At what stages would they flip back and forth? What you should find is that our derivative is then positive when x is greater than 8. Now, derivative negative then goes to positive. Then the area has a minimum when x equals 8. Lastly, to find our other dimension, we need to figure out, okay, well, what is y? Well, y was equal to 96 over x. That's 96 over 8. That's 12. Now, are x and 12 the dimensions of the poster itself? Well, no, right? You got to remember that the width of the poster is x plus 4. So the width of the poster in that case should be 12. And when it comes to our length, remember I had to add 6 to that. So I'll actually get a 12 plus 6. The dimension of that length should be 18. So a lot of stuff you have to be careful about here. It was sort of a rectangle within a rectangle issue. But at the end of the day, once you sort of deduce that, okay, well, this is just another rectangle, you walk through the process very similarly, do the work, get your optimization done, and it's not as hard as it looks like it is on paper. If you have more questions, just free to email me.